Okay, welcome guys to Physics 390 Class 3. This is on the TISE, or the time-independent Schrodinger equation, and its application to the infinite square well. And this will cover chapters 2.1 to 2.2 of our textbook. So we have the Schrodinger equation. How do we actually solve it? We've talked about what to do with the wave function so far, but we haven't actually talked about how to solve it. So here is the full time-dependent Schrodinger equation. Here, I won't read it out, but you can see it here. You've seen it before. And you'll notice that it depends on two variables, x and t. So it has two independent variables. And that makes it a partial differential equation, which makes it challenging to solve. So we do what mathematicians and physicists often do, which is we separate those variables. So we look for solutions which are products of a function of x alone and a function of t alone. So for example, big psi, which is a function of both x and t, would be little psi of x times little phi of t, where little phi depends only on x and little psi depends only on x and little phi depends only on t. So we substitute this trial solution into the full time-dependent Schrodinger equation, and trying the solution and doing some algebra, which you can look at in the textbook. It's a few steps having to do with, for example, when you plug in little psi of x, little phi of t here, the partial with respect to t acts only on phi and not, sorry, only on psi and not phi. So you get you're able to simplify things and divide through by the product of psi and phi and get a nice expression here. But you can check the textbook for the exact steps. So let's look at this equation, which we've got right here. The left-hand side, or LHS, as I've written here, is a function of t alone, because phi here is phi of t, and d phi dt, they only depend on t. Whereas the right-hand side, psi, little psi, and the second derivative of little psi with respect to x, plus v, which we assume only depends on x, is a function of x alone. So that means since we can vary t and vary x independently, in order for this to be true, they must both be equal to a common constant, which we call E. And when we set these equal to E, the common constant, two equations result. The second one is the TISE, or TISE, or the time-independent Schrodinger equation. And we'll look at that in just a second. But the first one that we get is coming from setting this left-hand side equal to E. So we then solve for the derivative of little phi with respect to t, just by multiplying up by phi, dividing by h bar, multiplying both sides by minus I, and we get d phi dt is minus IE over h bar phi. And that looks like an exponential, because it's the derivative is minus a constant times the function itself. So the solution is just this constant minus IE over h bar times t exponentiated. And this is sort of a harmonic time dependence, because e to the I gives sines and cosines. So we expect some kind of regular oscillation in time for that time dependence. The other equation we get, which comes by taking this part here and setting it equal to E, and then just multiplying through by little psi, is this equation here, which is almost as famous as the time-dependent Schrodinger equation. It's the time-independent Schrodinger equation. So you can see time doesn't appear here, and we can't, we don't know the solution to this until we specify the potential v of x. Okay, so for different v of x, for example, we'll look at the infinite square well. There's also the harmonic oscillator, different barrier potentials. So for different v of x, we will get different wave functions or little size and different values of e, which are possible. And we'll do an example of that on the infinite square well in just a couple slides. But before we do that, let's look at some interesting properties of these separable solutions. So the whole solution would be the little psi we get times the little phi, which we solved already as e to the minus I e t over h bar. So the first property is that these things are stationary states. What's meant by that is that the probability density is actually independent of time. So if we take the modulus squared of the full wave function, which is equal to the complex conjugate times itself, and then we plug in this expression here, little psi times this exponential, we get complex conjugate of little psi times e to the plus I e t over h bar, because we have to change I to minus I, times the function back again, which is psi times e to the minus I e t over h bar. But these exponentials will cancel because they sum to 0 and e to the 0 is 1. So we just get little psi star psi, which is the modulus of psi of x squared, which doesn't depend on time. So that means the probability density, which we get initially, remains constant in time. And that's why we call it a stationary state, because the probability density does not evolve or oscillate or otherwise change in time. And this same property that the exponentials cancel also holds if you calculate expectation values, expectation value of x or p or energy. You get that the expectation values are independent of time. So stationary states have time-independent probability densities, time-independent expectation values. The second interesting property of the separable solutions is that they have a definite total energy. So in classical mechanics, we call the energy the Hamiltonian, which some of you may have heard of. It's basically the total energy. And the Hamiltonian would be the kinetic energy, p squared over 2m, plus the potential energy, v of x. In quantum physics, this becomes the quantum operator, h hat, and hat means operator. It's kind of cute, hat being an operator, is equal to putting in the momentum operator, my I h bar d dx, we get minus h bar squared over 2m partial with respect to x squared plus v of x. So therefore, this is the quantum Hamiltonian operator or energy operator. So we can write the time-independent Schrodinger equation as that operator acting on psi, because if we act on psi here, we get exactly what we had on the left-hand side of the time-independent Schrodinger equation. H psi is equal to E psi. So this is an abbreviated version of the time-independent Schrodinger equation. H operator psi is equal to E psi. And then we can look at a couple of expectation values. The expectation value of H, the energy, would be the integral of psi star H operator psi dx. But H psi is just E times psi. So then this becomes integral of psi star psi, which is psi squared, and that's 1. The integral of that is 1, so we just get E. So the expectation value of H is just E, which is maybe not too surprising, but we've just verified it here. Similarly, the expectation value of h squared would be the integral of psi star h squared psi dx. And for h squared, we would take the first h acting on psi and get e, but then we'd have another h left, which would act again, giving another e. So we get e squared times the integral of the probability density. And so that's 1. So we get e squared. Okay, so why are we doing this? Well, we're doing this to show that the variance in the measurement of the energy, sigma h squared is the variance, would be h expectation value of h squared minus the expectation value of h quantity squared. And that's e squared minus the quantity e squared is equal to 0. So there's no variation in the energy as we measure the separable solution time and time again. Okay, so it gives a definite total energy. So we always measure the same energy for that. The third interesting property is that linear combinations of these separable solutions will give us the general solution to the time-independent Schrodinger equation, and also the time-dependent Schrodinger equation. So, for example, generally for the time-independent Schrodinger equation, we get a collection of solutions, not just one, but a whole collection. In fact, an infinite collection in general, which we label as psi nx. So it would be psi 1, psi 2, psi 3, on up to psi infinity, each with a different associated energy En. So there's psi 1 with E1, psi 2 with E2, and so forth. And we'll see a definite example of this in a minute with the infinite square well. So then the most general solution to the time-dependent Schrodinger equation, TDSE, can be written as a linear combination psi x and t is equal to the sum over all the time-independent, the stationary states, times coefficients weighting each of those stationary states. So this is the stationary state here. And if we weight them appropriately, if we choose these Cn appropriately, we can get any solution to the time-dependent Schrodinger equation we want. So most of those, if we have multiple stationary states present, so multiple Cn's not 0, we won't have the full solution won't be a stationary state, but we can make the full general solution as a linear combination of stationary states weighted by these coefficients Cn. So we can see that if we solve the time-independent Schrodinger equation for these separable solutions or these stationary states, that gets us a long way. That's our main task, because then we can write the general solution to the time-dependent Schrodinger equation as the sum here of a weighted average, or not a weighted average, but a linear combination with particular coefficients of psi n of the separable solutions. Okay, so that's 3 properties there. Stationary states for separable solutions, they have definite total energy, and linear combinations of them give the general solution. Okay, so let's move on to the infinite square well. So we imagine a particle which is free between 2 impenetrable ends at x equals 0 and x equal a. So it would have the potential v equals 0 between x equals 0 and x equal a, because then the derivative of v equals 0 is 0, so there's no force, so the particle is free. And outside of the well, and the potential jumps to infinity, which means that the particle can't get out because there's no way it could have enough energy to get out. So it's trapped inside. So here's a picture of it. You can see the potential is 0 inside from 0 to a, and it jumps up to infinity at 0 and a, and it remains infinity as we move to the left of 0 and to the right of x equal a. So it's called the infinite square well because it's looks square and because the potential is infinite on either side. Okay, so outside this well and at the positions x equals 0 and x equal a, we have psi of x equals 0. Okay, because there should be no chance of finding the particle. There's no way it can escape because the potential is infinite, which represents essentially an enormous or even infinite force keeping it inside the well. So there's no way it can escape the infinite square well. So the wave function should be 0 all the way to the left here, and at x equals 0 by continuity it should be 0, and then starting at x equal a and moving to the right it should also be 0. Okay, inside the well the TISE reads as minus h bar squared over 2m second derivative of little psi is equal to e psi. So you'll notice that we're missing the plus v psi here from before. And that's because inside v equals 0. So that term drops out. Okay. So this is a pure kinetic energy inside. There's no potential energy. So we can rewrite this as if we isolate the second derivative of little psi, we would get minus, if we multiplied here, minus 2me over h bar squared. And we call that 2me over h bar squared k squared, where k is the square root of that, or the square root of 2me over h bar. And the reason we do this is because we kind of recognize the form of this equation. This is like the classical mass on a spring or harmonic oscillator. We have the second derivative is equal to minus a constant squared times the function back again. So this has a general harmonic solution, which is psi of x is a sine of kx plus b cosine of kx. Okay, so it's a combination of sines and cosines with a coefficient out in front, and the k is the wave number here. So this is just what we would get for the classical harmonic oscillator, except that it would be t and omega. So here it's k and x, it would be t and omega for the classical system. Okay, so let's see if we can narrow this solution down a little further. Since we know that psi at 0 has to be 0 because the particle can't be at the boundary or outside the boundary, psi of 0 would be plugging in 0, a sine of 0 plus b cosine of 0. But sine of 0 is 0, cosine of 0 is 1, so we just get it's equal to b. But we know that this psi of 0 is supposed to be 0. So that tells us that b must be 0. So this drops out for this infinite square well as we've constructed it here. So so psi of x would be a little psi of x would be a sine of kx. Okay, so just the sine part. All right, so let's see what the other boundary condition, the fact that psi has to go to 0 at a, gives us. So with psi of x equal to a sine of kx, we have psi of a would be a sine of ka, and that's supposed to be 0. So there's a couple ways we could have it be 0. One would be if big A was 0, but that would mean that the wave function was 0, which would mean no probability at all. So there'd be no way to normalize it. So that's not a possibility. So it must be that sine of ka equals 0. And the distinct ways that can happen are if ka is equal to n pi. So if Ka is equal to pi, sine of pi is 0. If Ka is equal to 2 pi, it would again be 0, etc. Ka equals 0 pi would also work for setting this equal to 0, but then with K equal to 0, this would be uniformly 0 again, and we couldn't normalize it. So the non-zero and distinct and solutions that can be normalized are Ka equals n pi for n equal 1, 2, 3, and so on up to infinity. Or rewriting this a little bit and putting in an index for K, I'm just dividing by A, we'd have Kn is equal to n pi over A, where n is equal to 1, 2, 3, etc. So this boundary condition that psi at A is equal to 0 has restricted the values of K that we can have. It restricts the values of K that we can have to n pi over A, with n a positive integer. Okay, and this is what actually quantizes the system. This is why it's quantum mechanics, because we have only certain allowed values for the for this wave number, and as we'll see in a second, for the energy. So since K was defined as square root of 2m e over h bar, if we solve that for e, we multiply by h bar, square it, divide by 2m, we get h bar squared k squared over 2m. So that means if K has restricted values, the energy is going to have restricted values too, because the energy E is directly connected to K. So En would be h bar squared Kn squared over 2m, or plugging in for Kn, it would be n squared pi squared over a squared times the h bar squared over 2m. So this is the total expression for the energy of the particle with this index, or what we call quantum number n. So you'll notice it goes up as n squared. So the first one would be 1 times this quantity. The second one would be 2 squared, or 4. The next one would be 9. The next one would be 16. So the energies of the wave functions go up pretty rapidly in the infinite square well. Okay, so we said we wanted to normalize the wave function. Well, we can do that. We take a sine of kx and integrate from 0 to a, the psi star psi of that, which gives us a squared sine squared kx dx. And the integral of sine squared kx dx between 0 and a turns out to be a over 2. So that just turns out to be big A squared a over 2 is equal to 1. And then solving for a, we would have 2 over a, and then taking the square root, we get square root of 2 over a. Okay, which you might remember from modern physics. We worked on the infinite square well, and the normalization constant we found was the square root of 2 over the a, or the length. Sometimes it's also called L, depending on the textbook you're using. But the square root of 2 over the extent of the well, which we're calling little a here. So let's just take a look. So we've got the solutions. Psi n of x would be the a, which is square root of 2 over a, times the sine of kx, but k is indexed by n. Kn is n pi over a, so we put n pi over a here. We have sine of n pi over a x. So those are our solutions. We'll just take a quick look. You can see they're sinusoidal, so it makes sense that they oscillate. The first one would be sine of pi x over a, which when x goes to a becomes sine of pi, which is 0. And that's the first time it goes to 0. So it just goes up and comes back down. So it goes through one half oscillation. For n equal 2, it will go through, it will be equal to 2 pi. So if x is equal to a, and n is equal to 2, this would be 2 pi a over a, or sine of 2 pi. So it goes through from 0 to 2 pi, so through one full oscillation. And then psi 3 would go through 3 or 1.5 oscillations, and so forth. So as n went up, there would be more and more oscillations in the wave function. Okay, so a couple key properties of these solutions, which are pretty general. They're not restricted to the infinite square well, but it's a nice system to look at them. So one of the key properties is called orthonormality, which means if we take the integral of one of the separable solutions times another of the separable solutions, so indexed by m and n, we get either 0 or 1. If m is equal to n, we get 1, and that just corresponds to that wave function being normalized, because that would be the integral of psi n star psi n is equal to 1. If they're different, so if it was like integral of psi 2 star psi 1, they would, this little delta here is called the Kronecker delta. And if m is not equal to n, so and 2 is not equal to 1, that's 0. Okay, and this is a very useful property. It says that those are orthogonal, and since they're normalized also, they're called orthonormal. Okay, so that's one key properties of the solution. Another one is key property of the separable solutions is completeness. It turns out for any function f from x equals 0 to x equal a, okay, so on where the function can be non-zero, we can write that function as a linear combination of the separable solutions with the proper coefficient Cn. Okay, so this is called completeness because they form what's called a complete basis for functions on this interval from 0 to a. So we would write this as plugging in for psi n using just this formula here up in the upper right is square root of 2 over a sine of n pi x over a. And then the Cn weights each of those separable functions, solutions to the time independent Schrodinger equation by the proper amount to give the function f. Okay, and this is closely related to Fourier series because in this particular case, because the wave functions we find are sines, and Fourier series are building up functions out of combinations of sines and cosines. Okay, but this property completeness will work even if the wave functions are not sines, which we'll see in other examples this semester. Okay, so you might be wondering if we have a given f of x, so just like, I don't know, so just a straight line across, let's say, how would we find the function, the numbers, the coefficient Cn, which would allow us to represent it as a sum of these sines? Well, we use the orthonormal property, and we notice that if we take the integral of psi m of x, complex conjugate times f of x, we plug in for f of x as the sum from n equal 1 to infinity of Cn psi n. So just sum from 1 to infinity of Cn, which is a constant, so it comes out in front of the integral. Here's Cn psi n. When we integrate this psi m star psi n, remember that's 0 if m is not equal to n, and it's equal to 1 if m is equal to n. So that's represented by this Kronecker delta function, which is 0 if m is not equal to n and 1 if m is equal to n. So that would be equal to Cn times the Kronecker delta of m and n, which would be equal to Cm, because this would only be 1 if m was equal to n. So that would force n to be equal to m here. So to find the coefficient, we can integrate the function we're trying to represent by the particular basis function with the particular basis function psi m, and when we do that integral, we immediately get the coefficient that we need to represent it as this series. So in the textbook, our textbook, this is called Fourier's trick. So we can find the coefficients for f of x using the formula Cn. So I've just replaced m by n here. Cn is equal to the integral of psi n f of x, psi n star f of x dx. Okay, so to find a particular Cn, we would integrate the nth stationary state or separable solution times the function we're trying to represent, and that would give the coefficient we need to represent it as this series here. Okay, almost done. Just kind of to sum up here, so what have we accomplished? The full solution to the Schrodinger equation for the infinite square well is then given by this. It would be psi of x and t would be the sum from n equal 1 to infinity of the Cn, which are the weighting coefficients, times the stationary state. And this is the little psi n of x, which we solve for the infinite square well. And then this is e to the e to the I e t over h bar for that particular energy that we looked at before. Okay, but so if we knew the coefficient Cn, we would know the full wave function as a function of time, and that gives us all the information we need to get information about momentum and energy and position at future times. So how do we find these coefficients Cn? Well, we use the wave function at the initial time, psi x of 0, which is just a function of x, since it's at time equals 0, as our function f of x in the completeness property, which we just looked at previously, or Fourier's trick. So we would find Cn as the square root of 2 over a times the integral from 0 to a of sine of n pi x over a psi of x0 dx. Okay, so that's just what we had before, except we've plugged in square root of 2 over a sine of n pi x over a for psi n star of x, and we've plugged in phi of x and 0 for f of x. So that would allow us to represent psi x of 0 as this infinite series, and these coefficients would then apply to the at time 0, and then they would apply this time evolution given here would evolve the wave function in time. So once we find these coefficients Cn at time 0 using our initial wave function, we can plug them in here, and we get the full wave function x of t. And from that, we can calculate physical quantities like expectation values, probability densities at any future time t. So there's definitely some mathematics to do, but that's in principle what we do. Just to recap briefly, we've looked at the Schrodinger equation. We've looked at how we've separated into a time-dependent part and a time-independent part. We looked at some properties of the solutions to the time-independent part. We have looked at the infinite square well as an example of a manageable potential, which gives signs as its solutions to the time-independent Schrodinger equation. And then we've looked at how we can handle the general problem of finding the full solution to the Schrodinger equation by finding these coefficients Cn from the initial wave function at time 0. Okay. All right. Well, thank you for your attention. Next time we'll continue with the time independent Schrodinger equation, and we'll move on to the first part of the harmonic oscillator. Okay, so a different, it'll be similar setup, but different mathematics. So you'll get a chance to see some of this again, but in a slightly different context. All right, thank you for your attention, and I'll see you in class.